Okay, good morning, everybody. Ladies and gentlemen, it's a pleasure for me to welcome you at the webinar of the ELCOD project. Unfortunately, the current situation doesn't make it impossible for us to make another workshop as we did in the last years. That's the reason why we welcome you here online in our webinar. Let me give you a brief insight in what ELCOD is. Based on the long-lasting collaboration between academic partners from France and Germany, an idea was born about developing a low-cost, environmentally friendly and cost-effective long-range UAV. And then the name comes from endurance low-cost drone. So basically, the project partners of this consortium are people from the Offenburg University, namely the Institute for Unmanned Aerial Systems, from the INSA in Strasbourg, and the CNRS at the University of Strasbourg. Beside these academic partners, we have some associated partners in our consortium, Modelage Concept, In-Air Solution, Pôle Véhiculé du Futur, MaHyTec, and GeneSys. The whole project was funded by the INTERREG program of the European Union. And the main objectives of this project is to build, as mentioned, an high-endurance, low-cost drone, which is able to carry about 5 kilograms of payload, having a takeoff weight of about 25 kilograms, and which allows us to have about 100 hours of flight time and a range of about or greater than 500 kilometers. Beside that, we aim to have low environmental impact. That means a low CO2 footprint, which shows up in 2 alternative propulsion solutions for mid and for long range. As a first application, we aim to measure air quality and pollution indicators, as well as meteorological quantities. Beside that, there are a lot of applications possible, and during the project we developed a lot of ideas what else we can do with these endurance low-cost drones. At the end, the final aim was to build, not only to make a concept, but to build, test, and demonstrate these prototypes for ready for market solution. So after having this idea and just developing it, we were successfully in April of 2017 succeeding in having a funding option for this project through the INTERREG program, and then we started working on that. So we decided to work on 2 different concepts. One was a flying wing concept developed by the University of Offenburg. We will see later on these different designs in more detail. And a classical glider solution developed by the team of INSA in Strasbourg. So this results in 2 different build strategies, so different basic concepts, also with some differences in applications we had in mind, and this results in different building strategies. One was completely built from a wooden structure, and the other one with a fiberglass construction and molds. And so we will see that later on in the presentations of the 2 different designs, namely the stalk design of Strasbourg team and the Delta design from the Offenburg team. So here, already in April 2018, we were able to present the first prototypes of these different designs. You can see in the right, we have the Delta prototype, and in the left, we see the Stork design of Strasbourg team. And finally, starting in April 2018 and until June 2019, we were successfully doing maiden flights for the two different prototypes. We will see some videos later on where you can see that these are not just paperwork. It's something that is already in the air and is flying. So with the end of 2020 or early 2021, the project finished, and so the recent activities are just finalization and optimization of some parts. As mentioned before, there are some sensors and microfluidic devices that were developed in course of the project, because the main application we were focusing on in this project was air quality measurements, and that is something that was developed by the CNRS, the team around Stéphane Le Calvé. There are some finalization and optimization going on, as well as with the propulsion systems, both for the Stork and for the Delta design. In addition, we are happy to announce that there are two PhD theses starting now from based on this project. Two former students of this that were participating in this project are now starting their PhD theses on different topics, and they will present you more details on their topics: optimization of energy management for a fuel cell based drone, as well as studies on flex fiber and flex fiber composites used for building drones. And you will see more details later on. So that's it for the introduction. Again, a warm welcome from my side and from all the colleagues of the ELCOD project. And I will now pass the mic to my colleague, Mr. Kiefer from the INSA, to present the Stark drone. Thank you.
Thank you, Jörg, for your introduction. I will present you the project from INSA. Yes, I have to share my stream. Is it okay to everybody? Okay for us? Yes. So the idea for the team of INSA is to present you quickly the idea of the Stork drone. And first, I will present you the team at INSA. The team is composed of 3 research professors, me, Marc Védrine, François Gaeskop, 2 engineers and now PhD students, Martin Lefebvre, Thomas Pavot, 1 engineer and postdoctoral engineer, Anna Polino, 1 technician, Lou Rollin, and some master students. I will take Thibaut Wolf, Antoine Marie, Luis Miguel Sanabria Cruz, Camille Jörg, Simon Lago, and Vincent Jimenez. So the outline of my presentation, first I will show you the design of the Stork, the performances evaluation, the prototype conception, some flight tests, the automatic control optimization process, and the future of our project. And later we will have some presentation about different topics. So the first idea of the project was to design a long-range drone with a classical shape like a glider. So we have chosen a twin boom drone with a wingspan of about 5 meters, maximum wind loading of 150 grams per square decimeter, wing aspect ratio of 15, and a max power of 2000 watts for the electric motors. The idea is to embed fuel cell, hydrogen fuel cell with an electric propulsion, and to be able to integrate some component like pollution sensor from the CNRS. Here you can see a sketch of the prototype with wingspan of 5 meters. The actual mass of the prototype is about 16 kilogram without the fuel cell, and about 20 to 21 kilogram with the fuel cell. Concerning the estimated performance at the beginning of the project, we have estimated that the performance will be the consumption will be about 360 watts at 25 kilogram with a velocity of 19 kilometers per hour, and with an efficiency performances and the real consumption of the system. Here you can see a global assembly of the prototype and the different steps of building. For the field stage, we have chosen a classical way to conceive it in composite fiberglass and carbon by conceiving the molds on a master building foam composite, and the first wings are classically tooled by hot wire, and it will be composed of a sandwich of foam, wood, and carbon fibers. The wing joiner you can see here are providing carbon for the tests and for the final system. Concerning the system assembly, so we are able to embed a fuel cell of about 1000 watts from HES energy system, a tank, a hydrogen tank of 6 liters with a maximum pressure of 300 bars. The brushless motor will have a power of 2000 watts, and the weight I've said without the fuel cell is about 16 kilograms. Concerning the flight controller, we are using an open source Pixel 4 with the PX4 open source system with the GPS and so on. The power board has been designed by our team to be able to switch between two sources in case of failures, and the estimated autonomy the tank, the fuel cell, the system for the payload space, and all the electronic and onboard system. Okay, so yes, the first prototype we have done the first test of flight in May 2029, and the first we have done for the moment 21 takeoff and landing, about 5-hour flights, more than 300 kilometers of traveling, and with a classical cruise speed about 90 kilometers per hour. And finally, the power consumption has been measured in real flight at a mass of 20 kilograms, and with some flight test at 20 meters per second, and the real consumption was about 400 watts. And we have done some simulation with mechanical fluids, and we have estimated the total power of 300 watts at 20 meters per second. So by considering the motors and the propeller's efficiency, it grew to the 400 watts. The stall speed for the system with a mass of 20 kilograms is about 12 meters per second, so about 40 kilometers per hour. So during our campaign of flight tests, even if there is a limitation of COVID, we have tested the plane with different temperature from 0 to more than 30 degrees, and with some rain conditions, some good weather, some wind and crosswind, more than with a velocity of more than 30 km/h. So you can see some photos, and some photos in the fog here. It's foggy weather with low temperature and so on. So considering the typical mission we have done, the goal for the tests and the efficiency of the pollution sensor measurement will be to have a sort of grid with this kind of shape. With the global size of the system is about 1 kilometer by 300 meters. And the flight test has been done in electric flights without fuel cells, with a pollution sensor from the CNRS at 3 different altitudes, so for 100 meters, 150 meters, and 200 meters. And the cruise speed will be about, has been about 20 meters per second. Another topic of our work is to do a dynamic control modelization of the drone to be able to estimate the result with a real flight compared to the simulation flight with the same real flight inputs of the system. And I will show you that later. And to conclude my presentation, we are working on the evolution of the Stork Mark II. The idea is to optimize the aerodynamic of the system by using molds for the wing, for the tail, and for the fuselages. And the topic is to design the first biocomposite UAV with a fuel cell system. And the work is always focused on hybridization of the fuel cell, battery, and package. Thomas and Martin will do their presentation about these topics. So the final design will be a 2-boom drone with motors and sensor integration, a wingspan of about 5 meters, and the final system will be done in flax and carbon fiber design. The cruise speed will be estimated to about 90 km/h, and the maximum takeoff weight 25 kg and max payload 5 kg. Here you can see an overview of the CAD of the Stork MK2, and for the moment we have tooled all the masters and built 2 of the 4 molds of the wing, and we expect to finish it at the beginning of next year. So to conclude, in spite of the context of COVID, the project followed a normal evolution, and we could propose at the end of the project 2 PhD theses, one PhD from Thomas Pavot concerning the optimization of the fuel cell system and the hybridization of the system. It has begun the 1st October of this year, and Martin Lefebvre is working on a biocomposite system, and his thesis has begun 1 year ago. So the work from our team still continue. We are working on autopilot redundancy work, the optimization of the flight, the communication system, to stock building process to be able to have a versatile system that could be replicate quickly. Thank you. Yes, so Bernard,
yeah,
you can have your speak and share your stream. I give you the authorization.
So
you can do that. Okay for you.
Okay. So well, here we go. And here we have a presentation. That's okay with you?
Yes, you have to split to
Okay,
full
you can
screen.
see that?
Yes,
It's fine.
yes.
Okay. So I will talk about the Delta drone. You can see a picture of it. It's flying wing, Delta type. And this is actually the aerodynamic model. It's not the final one. And it's the final one is differing in the size of the nose because the engine is pretty large. Well, pretty early in the project, it became clear that if we would use a fuel engine, the main issue is to get as much fuel as possible into the aircraft. It's not so much about aerodynamics, but about the amount of fuel you can get into it. The reason is that fuel engines don't reduce the fuel consumption as much as electric engines with better aerodynamics. So the optimum is at a somewhat different operating point, which means we need another aircraft frame, and we came up with the Delta Flying Wing, and it has 4 ailerons with 4 servos, just for redundancy. Can be flown with 2, obviously. It's pretty agile and robust, and it's designed for 10 plus minus 10 G load capability, which a flying wing agilely flown easily can get. As is typical for low aspect air ratio wings, there's a low gust sensitivity, and because we have a fuel injection system, there's a pretty good altitude capability, somewhat about 5,000 to 6,000 meters estimated. We also introduced a de-icing system in the nose of the profile on the leading edge, because there was some intention to fly around Iceland, and we have internal heating of the system of the aircraft, so the heat of the engine will be forced through the internal of the aircraft. The servos will be heated, and part of the cooling will be done by the wing surface, reducing the resistance or the impact resistance due to cooling air. And there's pretty large fuel tanks, actually 2 in each wing. And I don't see my own things here, and the large whatever. Yeah. So it says I have to close this one here, probably, I don't know. Let's see. Has a later bay, that's what it is. So the structure is made of wooden and will have a kekonite covering, pretty traditional. And the cowling is made of ABS. And so it's simple to manufacture and repair. And well, there's another word I can't read. It's low cost. So there will be a wooden propeller on a 50 cubic 4-stroke engine with fuel injection. Stefan Steiger will talk about the fuel injection system, and the engine is pretty heavy, so we have to, but it consumes very low amount of fuel, and so this was the optimum for range and flight time. For communication, the Iridium satellite communication will be used for long range. Well, takeover weight is 25 kilograms. It should fly up to 33 kilograms with reasonable performance. The empty weight is 15 kilograms, including the engine. So there may be room for payload and full fuel. Wingspan is 2.56, cruise speed around 110 kilometers an hour. The payload bay volume is in the middle in the CG. It's 30 centimeters in length, 26 centimeters in width, and 20 centimeters in height. We have two 7-liter wing tanks. It's in total, it's 10 kilograms of fuel. With 300 grams per flight hour, it would mean 33 flight hours and about 3,000 kilometers range. Takeoff is bungee and belly landing. That's the idea with it. So this is a picture of the Maiden Flight, which was in October 2018. And we measured descent rate versus flight speed up to 160 kilometers an hour, and the best glide ratio was about 13. It has excellent stall characteristics due to the dog tooth. You just can hang it onto the prop and fly it, so it stays stable. But with the, as already said, with a fuel engine, the glide ratio is of minor importance. The fuel capacity is a major issue. Here I have some impressions from the Kiel flight test in 2019, and this is it has been done in on the Kiel airport, and you see the start wagon with the delta on the start wagon. This is our safety pilot Kurt, Stefan. Here we have Raimund, flight engineer, on the computer. Here, again, the team, some waypoint programming, things like that. And this is Jörg Fischer. He did quite a few simulations for the flight control software. And actually, it was one day it was raining, so we stepped into our trailer. It was better. Right here, you can see how a start sequence. So you see the delta at the bungee, because we want, in the end, we want to have to start with a running engine, because the fuel engine has to be running. We had a mechanism to avoid the propeller cutting the bungee, and so you have to draw the thing backwards, and then on the right side you see the delta starting on the runway, and then it takes off, and well, it's in flight, throwing away its mechanism there. And here you see the delta in automatic flight. We don't add up all the kilometers we flew, but there was quite a few flights. And here is the delta in the automatic landing procedure. And that's about it. And so we made quite a few fully automatic flights from takeoff on the start wagon to waypoint flying, loitering, and automatic landing, and optimized the parameters a bit. So the flight tests in 2000 with the fuel engine were just another COVID victim. Well, thank you. And I have a video for you, if you like, so from the Maiden Flight, so you get some impression of the flight characteristics.
Thank you, Werner. I will now, for the break, show different videos, a video from Werner's teams and a video from the INSA teams. So I have to share my screen. Werner, you want to show you, to do your video, or I can?
Yeah, I can start that if you like.
As you want, it's a problem.
Okay, let's see. I have to go to this one. A lot of knobs. So maybe you don't hear the noise, but it's not. So this is hand flown actually by Kurt. Bungee takeoff, 12 kilograms, Take a wait. So this is around 160 kilometers an hour. So it's only a 900-watt engine, and the fuel engine will deliver up to 1.6 kilowatts. So this is Maiden Flight. Because with Maiden Flight, you obviously don't know the stall characteristics. The pilot made a fast landing. You can see that. Okay. So that's
Thank you,
my part today.
Thank you. For now, I will show you some videos, some official videos from the ELCOD teams, the ELCOD store teams, and the ELCOD Delta team. So I will share my screen. Normally, it's possible for you to see it. It's okay? I will show you the videos from the team of the Hochschule. Normally it will work. Yes. Okay, you can see the screen. So I think we have time for some little question if you are. And if there is no question, I can give you speak to Stéphane Le Calvé in charge of the pollution sensor system. Stéphane, you are ready?
Yes.
Okay, you have the authorization.
Okay, thank you. Share. Is it okay?
Yes, done.
Can you see my screen? Oh my God, it's too. I would like to enlarge the screen, but. Yeah, it looks better now. Okay. So in the framework of the ELCOD project, we are developing a sensor to monitor outdoor air quality. So this is a staff list of IPES who work on the project. So Christina, Pauline, and Anaïs are engineers in analytic chemistry at CNRS. They work on air quality sensor calibration and evaluation. They did also the conception, so rapid prototyping, and they did the experimentals, the experiments under the laboratory condition. Pauline was engineer internship at CNRS, so she developed electronics and software, and Christophe helped her to do this development. And myself, I did the coordination of the project. So VOCs, volatile organic compounds, are oxidized under light condition to produce photochemical products such as ozone, halides, peroxide acetylnitrate, and nitrogen dioxide. So this set of reaction need also some nitrogen monoxide to produce these pollutants. So the objective of this project is to monitor ozone, which is a key product, NO2, NO, and VOCs by means of different sensors, which are listed on the. We have listed all the pollutants here in the table. So the objective is to have a multi-box sensor or multi-sensor box with a good autonomy, a low cost, low dimension and weight, to have a accurate monitoring. Here are listed the range of concentration we expect to get. So basically it's up to 1 ppm, so 1000 ppb for VOCs, ozone and nitrogen dioxide. And also we would like to monitor the temperature, the relative humidity and the pressure, because all of them can have an impact on the sensors measurements. It's here. It's a general overview of the box So basically, we sample air through a micropump. This air is gently heated up to 30 or 40 degrees, and then it's injected in a gas-tight tunnel where all the main sensors are installed. Here we have two valves to close or to open this tubing or this reservoir, and then we have a second box where are placed the remaining sensors, so the pressure, temperature, and relative humidity sensors, the VOC sensors, and the sensor to monitor CO2. So here first we have developed, we have selected the sensors. So we can see that all of them here are similar. And then we did the mechanical integration. So first we design the box according to the size of the different items, and by using CAD, computer design, and we use Autodesk Inventor software. So in this configuration, you have the FSN tunnel here, where with the 4 sensors. We have the 2 valve here and here, the heating system here, the 2 batteries, which can, with these 2 batteries, we can get 4 hours of autonomy. We have the main electronic cards here, and the additional sensor cards in this box. And finally, we have the screen in the front of this box. So in terms of electronics, we have divided the electronics in 2 parts. We have the main electronic part here. So this is I don't see if you can see my mouse.
Yes.
No. Yes, you see. Okay. So basically, this permit to control and to save the value recorded by the 4 main sensors here. This data are commented by ADC, and they are displayed on the screen here, and they are saved on a SD card here. With this electronic card, we can also control the pump, even the speed of the pump, and the 2-way valve, and also we can also manage the 2 batteries and the voltage provided by the 2 batteries. And the additional sensor cards, we decided to separate it because we need to have a gas tight box to install all these sensors, and we put the pressure, temperature, and humidity sensors, the VOC sensors, and some some additional sensor as well, like CO2. So in terms of software, we have developed a very small software to monitor, to display the data on the screen and to save all the data in a table, in a file, in a CSV file, saved on the SD card. So this is the screen of the, and we can change the, we can switch on the different components, so NO2, ozone, nitrogen monoxide, and so on. And here we have an example of the data for NO2. So we have the time, we have the concentration, we have also the working, we have also the raw data, which permit to retrieve the data after, so post-processing the data after they are saved. So this is a two picture of the final prototypes. In fact, we have three prototypes similar to this one. So we have here the front part of the device, and we can see that it's quite compact. And in this picture, we can see that we have installed the micropump at the bottom, on the alpha sense tunnel here, and we have all the additional sensor card, which is installed into this gas tight box here. We have the main electric card, the two batteries, and the Arduino screen, and some cable as well. So once we have developed this multi-sensor box, we need to calibrate and to validate the sensor response of each sensor. So first, we need to generate a known mixture of gas. So we use other generator. We use also some gas mixture of NO2, NO, CO, and so on. And we use air for dilution. So basically, with this setup, we can generate calibration mixture from a few ppb up to more than 1000 ppb for each company. So this gas mixture injected into the gas tunnel here, and we can monitor the response of the sensor. Here it's an example for ozone from more or less 1000 ppb down to 24 ppb. So we have a decreasing response depending on the concentration here. And this is the raw data we obtain for the ozone sensor and the NO2 sensor, depending on the NO2 concentration generated in the mixture. In fact, so NO2 sensor as a response to NO2 concentration is quite normal, but the ozone sensor has also a response to toward these compounds. So we need to subtract this response when to monitor the ozone values. This is the equation used to correct the ozone concentration with NO2 measurements. So finally, we did some calibration. Here, this is the ozone concentration measure versus ozone concentration generated for two devices. So the first one, the blue one, is the ozone sensor, and the red one is the Oriba analyzer, which can be considered as a reference for the ozone monitoring. And we can see that we have a very good agreement. We have only 13% of difference between the two instruments. So once developed and validating under laboratory condition, we can install this instrument into the drone for flight tests, at least for preliminary flight tests. And we saw that we recorded the values during the very short flight. And we measure the pressure according to the altitude. So this is the takeoff, the measurement at the takeoff, the measurement at 100 meter of altitude, and so on. And this is the value at for the landing. So we saw that we have some small problem because the instrument were switched on only a few minutes before the takeoff, and in fact we need at least 30 minutes to stabilize the values before the takeoff. It will be necessary for future flights. But we also measure the ozone values here, and we saw that in fact the measurements here are very close than the average ozone value measured in the free troposphere, which are equal to 40 ppb. So in general, so I think it's a very good agreement because the measurement looks close to the expected value. So in terms of conclusion, we have made the conception, and we have designed the multi-box sensors, multi-sensor box, sorry. The sensor were selected to reach PPB level. Sensor integrating on Arduino. We have successfully developed the mechanical, electronics, and software parts. Sensor of air pollutant was tested and calibrated for ozone, nitrogen oxide, like NO2 and NO, carbon monoxide as well. For ozone, we did a comparison with the reference analyzer, which is promising. So we have fabricated 3 competency sensor devices. We have also did a demonstration during the preliminary flight. More flight are needed to get some data. I think it could be possible after the health crisis. And in terms of perspective, we expect to integrate in some sensor to monitor particles in the range 0.3 up to 20 micrometers. Thank you for your attention.
Okay, Martin. Yeah, thank you. So, hello everyone. So I'm Martin Lefebvre. I was a mechanical engineer on the when I was engineer on this project. I was in charge of the CAD and mechanical testing. Here you can see. Can you see the second slide?
Why? Try it again. There's a little problem on our presentation, but yes. Sorry, there is a little problem. It's okay, I think. Okay. Okay. Yes, normally it should work. No. It's okay for you? Yeah. Yes.
Yeah, okay. So now it's working. I'm sharing the screen. So I was in charge of the CAD of the prototype, the first one, and now I did the CAD of the Mark II drone. So I can see the CAD with twin boom composite structures and 2 monoblock wings. And the idea of the CAD is also to do the sketch and to. Yeah, the screen is not at a good size. So I think it's not. Okay. Yeah, I do apologize for this. And the idea is to use this CAD to do the master and the mold of the drone, because as Renaud mentioned, at the beginning we did it as a conventional way, and now we want to produce mold for a small industrial process. Fabrication with computer, and after to use machining, we went to a college in Strasbourg to manufacture all the master. And at the end we have the last picture. You can see that the mold, the master of the drone are finished, and we still have some steps I will present you just after. And the idea of this process is a low-cost process because we use MDF. It's a medium density fiberboard wood, and it is a process that we didn't see in the past. So it's a good investigation to use this low-cost process to manufacture the master. After the master, the machining, we have a lot of steps to have a mold. The first one is to paint the master and to polish and to gel coat. And you can see after all this process with our colleague that is working on the mold. And the final step is with the mold, to manufacture the final version. We finished 4 molds on 8, so we are basically at the half of the manufacturing. And the idea of the mold is we can, after build many versions. The first one will be the composite carbon fiber structures, and the next one will be with flax fiber. This is a good transition with my PG project. And this is the future work that we have to do on the MK2 project Stork drone. As it was mentioned at the beginning, my PhD project was about how to replace glass fiber to flax fiber and to design the world's first long-range bio-based UAV. ELCOD was an interesting project because with Thomas, it's our graduation in INSA and after the beginning of our PhD. So it's a very interesting project. The field that I'm working on, it's about composite manufacturing, composite testing, and finite element analysis. So I'm CFD, but most of my work is about structural analysis. We'll see later. And with my team in also the scale about the microstructures. I will talk about it later in the presentation. Why it's interesting to investigate about flax fiber. As you can see, it has very low carbon footprints because, as Jörg mentioned at the beginning, we want more eco-friendly drone. So also propulsion and material is an interesting way to investigate. As you can see that compared to carbon fiber and glass fiber, flax fiber are very low global impacts. And the second point on the chart of the left is the flax fiber has compare properties to glass fiber relative to density. I mean, you see that carbon fiber is very strong and very light, so very good properties. But compared to aluminum and titanium that are more heavy, there are less ratio, this strength density ratio. And when you use in aeronautics, it's very interesting to compare this ratio. That is why back in the past, the Concorde was made in aluminum. And now with Airbus and Boeing, they use more, half of the plane is made with carbon fiber. So we hope for next year to have the Stork drone made with flax fiber. It's also a second point because we want low-cost process, low-cost drone, and when you see the cost euros per kilograms, flax fiber is comparing to glass fiber, and it's cheaper than carbon fiber. Now the earth of my PhD project is simulation on flax fiber. Why it is important to do simulation to avoid disintegration. As you can see, when the lift is too important and the deformation is too big. And this is why it's mandatory to do a test and simulation on the wing structure. It's what I am doing on this project. So I can see the wing. The spare, the skin, at everywhere. I put the simulation to 12G because it was a book of specifications at the beginning of the project. We have to, the failure has to occur after 12Gs. And there's some results that I have with simulation. The first one, I will compare carbon fiber and flax fiber. The first one here, as you can see, is the full line is a carbon fiber. And why I'm investigated is the etching ratio. If you are working composites, it's a very interesting ratio. It's when this ratio equals 1, you have failure of the composites. Me, because I'm working with UAV, I have to add a kind of security coefficients. This is why the red line is a maximum line to where the failure can occur. And you can see in the abscissa is the load factor. When the load factor increases to 10, 11, 12 Gs, the structures is converging to failure. And then comparing the wing skin in yellow, the wing spare in purple, and the wing joiner in green. We can see that the wing joiner is designed to be strong enough to 20 Gs, so it's perfect. And the carbon fiber skin has to be strong enough at 10 Gs. So with carbon fiber, we will reach the result of to not have failure during the flights. But after I try to input flax fiber and see the results, it's in the line. You can see that the wing joiner can still resist to close to 18 Gs. The wing spare and carbon also around 10 Gs. But when you replace carbon fiber by flax fiber, you can see that the skin can only resist to 4.5 Gs. So this is drawbacks of the flax fiber, and this is also one of my objectives is how to use flax fiber but to resist close to 10 Gs on the skin. And so you have to determine the best flax composition of the composites. And to optimize simulation and to design the drone, now I am doing some testing on the composites. First, I did some static mechanical tests. It's a case of constant flight. But in the following months, I will try to investigate about dynamic testing. For example, for the wing in case of wind gusts, impact of bird or ice, and also for crash. It's a mandatory for automotive or airplane to design in dynamic testing. This is the scale of the composites, as you can see with the first at the beginning of the presentation. And now I am also investigated at the scale of the technical fiber. As you can see, we just did test. Here is a small fiber, technical fiber, and we did tensile tests on this fiber. It's also interesting to do static testing and dynamic testing that we do in the following months. But the biggest problem with technical flax fiber is the high variation in the mechanical properties because the diameter is not very constant and there is high variability on the diameter. That is why the future work of my PhD that will start next January will be to not to investigate about the technical fiber, but to isolate elementary fiber and to do tensile tests on this elementary fiber. So we did tests on a fiber with average 100 micrometers. And the next step, next month, will be to do tests on a 10 micrometers fiber. We hope that we'll avoid tensile variability. And also, it's very original publication. We have to do very good publication because we didn't see publication about the impact of temperatures and dynamic testing on this fiber. So we have to do very interesting research about this flax fiber. Thank you for your attention.
Thank you, Martin.
Thomas.
Thomas will present you now the electronic and electronic and his PhD thesis subject.
So, hello, I'm Thomas Pavot. I was an electrical engineer on the ELCOD project, and now I'm a PhD student. I will come back later on this point. So I will present you the electrical design of the Stork drone. We have two LiPo batteries, 4S in parallel, which are the main power supply of your UAV. Batteries provide power to the flight controller. It's a PICSOC, which assures the control of the Stork. The power module in purple is a DC-DC converter for the PICSOC and send data about voltage and current from the batteries. Around the PICSOC, we need the components such as GPS, compass, piezoprobe, telemetry, LiDAR for altitude, radio receiver, to have data enabling the PICSOC to control the UAV. Anna will talk about this after me. In order to ensure redundancy, we have provided a backup battery to power the flight controller and all control surfaces in the event of a failure of the main power supply. The interface board allows switching from one power source to the other in case of failure. It also allows PWM signal to be transmitted to the various control surfaces. We have 8 control surfaces, different control surfaces, and the motor. Now I will talk about the communication system. With the drone, we would like to have a link everywhere between the drone and the ground station. For now, we have flown with classical telemetry module, which has a range of 1 kilometer. Of course, we want to fly for several hours and at a distance of 100 kilometers or more, for example. For this, we need to develop a long-distance communication solution. Our idea was to use a mix between GSM and satellite communication. The best solution is satellite because we can have the link between our ground station and the UAV everywhere, but it's very expensive. So for flight where we can have the GSM network, we will use it in priority. During this project, we developed the GSM solution. The interface between the flight controller, the PIXOG, and the GSM module is made using a companion computer, such as the Raspberry Pi. The data is sent and stored in a database hosted by the ground station, and we can track our drone in real time and on the ground station. We can also send an order from the station to the drone, such as return to the launch, for example. This system has been tested and works on quadcopter. Now we need to integrate the system on the stock. One of the objectives of the ELCOD project was to see if a fuel cell could be used to power the UAV. We bought a 1000 watt fuel cell from HIS Energy System, and we built the drone in order to integrate the tank and the fuel cell in the fuselage. We have not conducted flight tests with the fuel cell for safety reasons, but with a consumption of 450 watts, the drone is able to fly around 5 hours. However, we did some tests with the fuel cell on a test bench equipped with the UAV electronic speed controller, the motor, and the propeller, in order to be as close as possible to the flight condition. We pushed the power from 0 to 1600 watts at full power in order to simulate a takeoff. We did several tests lasting about 30 minutes and one test lasting more than 1 hour at 500 watts. And we noticed a problem, an issue with the fuel cell. We had a voltage drop every 10 seconds from the fuel cell caused by the purge. During this instant, the LiPo battery takes over, but the LiPo voltage is lower than the fuel cell voltage. This leads to a drop in RPM from the motor. This problem showed us that hybridization was not optimal between the fuel cell and the hybridization. So with this idea, we choose to start a PhD. Now I am doing a PhD named ELCOD for Hydrogen Endurance Low-Cost Drone. This PhD started in October and will finish in 2023. The title is Optimization of Energy Management in a Drone Equipped with a Fuel Cell-Based Hybrid Source. So on the left, you can see our current system, and on the right, what I want to do for the PhD. On the left, you can see two different sources of energy, the fuel cell as primary and batteries as secondary. In blue, it's the electrical card, which is able to manage the power supply for your drone and the electrical motor. So when we have less than 1000 watts, we use the fuel cell. And for example, at the takeoff, when we need more than 1000 watts, the system sums fuel cell and batteries power. As we mentioned before, we noticed an issue every 10 seconds caused by the purge of the fuel cell. So batteries provide the power. We have a current peak on batteries regularly, and we listen to the issue with a drop of RPM from the motor. So for the PhD, we would like to improve the system with the conception of new hybrid card, which is able to manage 2 or more than 2 energy sources. We can think about adding a supercapacitor or a photovoltaic source on the wing. And with this card, we will manage how we spread the energy to the load without any effect on it. We would like to use a new strategy for the command of the electronic card as for example, optimal control or predictive control. I will present you my work plan for the PhD. So first, I need to know maximum things about hybridization system and energy management strategies. So I am doing a state-of-the-art and I find hybrid system in, of course, electrical vehicle and also for uninterruptible power supply. After that, I will modeling my different energy sources, fuel cell, supercapacitor, batteries, and the drone in the point of view of energetic system. With this model, I hope to be able to test control strategies as predictive or optimal control and develop an electronic car. And at the end of the PhD, we would like to implement this and test your system to measure the efficiency compared to our current system. So that's my goal for the PhD. So I'm going to let Anna speak about these works.
Good morning, everyone. In the following, I will be talking about the modeling and the automatic control of the drone, particularly the attitude control and of the drone's torque, and basically explain in detail what was the train of thought and some of the results we have had throughout the ELCOD project. So if we are interested in proceed with the automatic control of the drone, first we have to consider some prior steps. First of all, we have to provide a mathematical model of this drone. Then we validate this model by building a flight simulator. And this flight simulator is also a platform for, in the following, tune the controller. So talking about the controller, my colleague Thomas Pavot has presented this scheme of the PX4 controller, and we have some strong motivations for using this platform. First of all, it is an open source and off-the-shelf product, which can speed up the controller is also architecture portable. So in case we would like to use different types of drones, we would be able to do it. And we are able to implement different control strategies, such as manual, stabilized, loiter, at altitude, mission, and so forth. And what's interesting is that many of these strategies come pre-programmed. I will be focusing primarily in two types of control, the position and the attitude controller. We can consider them to be in layers, the position controller being the outer layer and the attitude being the inner one. So once we want to make the drone fly on a given trajectory, we can set this prior to the flight in a ground station, giving, for example, trajectory waypoints. And once this is pre-programmed and the plane is flying, the position controller receives these waypoints from the ground station, and it computes references for the lower level control, the attitude control. And it receives feedback from the plane so that it can correct the drone position and ensure that the trajectory will be followed. Then we have the attitude control that receives the attitude references from the position controller, and On its turn, it computes the required control surface angles. That means it controls how much ailerons, elevator, and rudder must deflect. And it receives feedback from the plane so that it can correct the attitude angles so that later on the position can be also ensured to be followed according to the project. So, as I said, PX4 controller proposes different pre-programmed controller architectures. And here I have brought the attitude controller architecture from the PX4 platform, PX4 website. And what we see is that here we have the controller, but the controller cannot function by itself. It serves to make the system, the drone, work in a desirable manner. So for that, we also have to propose the values of the control parameters that I have highlighted in red, and they must be provided so that we reach to desire optimal flight and optimal behavior. This is what we call the control tuning, proposing these values of parameters of the controller. But for us to tailor a controller is good for a given system. And therefore, some knowledge of the system is fundamental. What we call the obtention of the system model is called a system identification, and I will be detailing this in the following. So for us to do the so-called system identification, first we have to choose a mathematical model, and then we have to collect data from the aircraft and try to stick this data at its best to the mathematical model. So with considering certain simplifications, such as considering that the axes of the airplane are decoupled, we can reach this mathematical model. And here I have highlighted that there are two unknown parameters, and we are going to collect data from the aircraft and try to make these parameters fit at its best to the we have used. It is the in-flight method that actually uses flight data, and the off-flight method that uses a virtual aircraft model. So the first identification method is this in-flight method. Here I have the roll movement through the movement of the ailerons. And what we do is that the pilot inserts arbitrary signals in the ailerons and exclusively in the ailerons at different times. So here I have brought 4 examples of manual signals given by the pilot to the ailerons. So we consider that each of these entries is an experiment, and we compute transfer functions for each of these. And then we apply a method to find which is the best transfer function that is able to characterize the whole envelope of experiments. On the other hand, we have the off-flight identification method, where we create a virtual model. Here I have brought an example of the model we have used within the software XFLR5. This software allows us to run several analyses, and the analysis that is particularly interesting for us in the system identification step is the airfoil stability analysis. So once we run it, we obtain several data and specifically aerodynamic derivatives, and these aerodynamic derivatives enable us to compute this transfer function, because the coefficients k and p, they are dependent on this derivative. Here I have brought an example of the comparison between these methods, particularly for the coefficient k. So here all the points in blue and the tiny point in red are flight experiments that so after the identification process, we have come of this possible different values of k. And after running our optimization algorithm to find which would be the best candidate, we have found that the best candidate to reproduce the behavior of all the flights is this red point. This data has also been extrapolated to all the airspeed envelope considered. And the data in green, as well as this point, relates to the off-flight method. And this method has also been extrapolated to all the airspeed envelope. So what we have as positive concerning the in-flight method is that it is actually based in the real plane, so there is no approximation in the structure of the plane. And it's also an airspeed dependent method because we take into account all of the blue points to find a best candidate that would reproduce as simply and as good as possible the set of previous flight experiments. As the drawbacks, we can highlight that it's pilot and sensor dependent. So particularly for the matter of sensors, if we have any default in the sensors, we don't have data of good quality. If the pilot doesn't excite the dynamics enough, we also might not have good quality data. On the other hand, we have the off-flight method that allows us to obtain some results in the design phase. We don't even need to have a ready drone to already obtain some data concerning the dynamical system. But on the other hand, we have a single airspeed model. That's what the software we have used provide us right now. And this data is also possibly further from reality because the mass distribution in the simulation can be different and the masses themselves. So there are differences between the real plane and the simplifications that are comprised in the simulation. So once we have an identified system, we can insert it and develop a flight simulator. And the interest of it is that we can evaluate the aircraft behavior in some configurations that have not been tested in real life. For example, we can test several different types of controllers, and this can save us time, effort, and energy. So what we want to do with it is to compare it, compare our simulator with the real flight tests so that we can ensure that our simulation is actually reliable as well as our identified system. So here I have some sensor readings, the manual inputs from the pilot. In the middle, we have the control law that has been translated from the PX4 firmware implementation to MATLAB. Then we have the airspeed dependent identified system, and we also try to implement some noise emulation because, after all, the real airplane is subject to wind gusts and some other disturbances that we might not take into account in simulation. And here we have, in all to the right, two ways of checking and comparing the real and the simulated behavior. that means to tune the control law. And recalling the design of the controller that I have exposed to you a couple of slides before, we have these unknown parameters, for example, P, FF, PI, and some others. They must be provided for a good flight, for an optimal flight. But then an important question is, what is actually optimal? And it actually depends on the project. We can consider that optimal is when we have a fast response time, or if we have limited energy, and that's the case of the drone, we would like to prioritize a limited control energy, or we can consider the disturbance immunity, or even the robustness to unmodeled dynamics. Some of these objectives, for example, response time and limited control energy, they are an antagonism. So we actually have to choose a trade-off between these objectives. For working with this trade-off and finding the good parameters for our project, we have used the H-infinity method. In this method, it works such that once our requirements are chosen, this method points out whether the requirements are feasible or not, and which is the safety margin that we have until we reach the undesirable behavior. And these requirements, response time, limited control energy, and so forth, they are written as a frequency function. And this frequency function must either remain under a certain value and be bounded by a given behavior. And here I have brought an example of what it actually means. So if we're talking about the limited control energy, we have the interest of some curve that behaves more or less frequentially like this. So in the high frequencies, we want that the control attenuates its outputs. And this is interesting so that we avoid because we must consider that once we identify a mathematical model, there is always some unmodeled dynamics because we were looking, first of all, at a simple model. So I have shown that our controller has a fixed structure, and a fixed structure cannot do everything we want. We cannot ensure too many requirements. That means we have to prioritize some objectives, and then we simulate to verify if the flight behavior is satisfactory or not. Here I have brought two examples when where in the first column we prioritize response time and disturbance immunity, and in the second column we prioritize limited control energy. So when we verify the control inputs that have been generated, it is true that when we actively limit the control energy and we state this as a requirement, we actually obtain less energy in the control. We also see that in the left side, we have a control input that is very noisy and of higher amplitude. And this is particularly not interesting for a drone when we are favoring endurance. Once we compare these two curves, then we have to check, is the angle displacement in the advantageous control input, is it satisfactory? If it is, then we can prioritize the second behavior over the first one. So thank you very much for your attention. Yes, I would like to highlight that well, I didn't present the future work for this, but among the future work, we can envisage would like to perform more experiments as well to try the different control laws. And unfortunately, we couldn't do that because of the pandemics. But we were able, with the results we have gathered so far, to publish one paper in the IMAV conference. And I hope we'll be presenting some videos or some material in the following about this conference. And we are also preparing a second paper where we show some results, particularly in the control tuning that I have discussed in the end of the presentation. Thank you.
I will quickly show you a video we have taken at the IMAP competition. We used to participate to the IMAP competition every year with the students, the PhD students. Why? Because IMAP is a very interesting competition. It includes competition and a scientific part, so it's possible to present some paper and to participate in the competition. So the idea now is to present you a sum up of what is an IMAP competition, and we have yes, and we have participated to the outdoor part of the competition. And last year, the INSA team has the third place at this competition. So I have to share my screen. Sorry. Okay. Okay, yes. Yes. So, thank you. So now the IMAF competition has been scheduled to next year normally. So we hope to participate to the competition next year because of the pandemic. Thanks for your attention. Do you have any question concerning this competition or the other topics for the moment? If there is no remarks or question, I propose to Stefan Steiger to present the Delta 4-stroke motor optimization. So, yes, Stefan, I will give you the possibility to present. It's okay for you, Stefan.
Okay, yeah. Okay, hello everybody. I want to give you a small overview over the optimization of the 4-stroke engine where we like to use in the Delta Ring. At first, the content, our 4-stroke engine is from Honda and it's called the GXH50 engine. At first, we look at it in the standard configuration. Then we show a little bit about the modified engine or the optimized engine. Then how we test the engine, and at the end we show some test results. So the engine in standard configuration is a normal 4-stroke engine. It's a big engine and it's also a heavy engine. This engine is designed normally for work on ground, not in the air. It's designed for long lifetime. Normally use it for electric power supply stuff, like or for pumping stuff. The weight here you see is 5.5 kilogram, but he has a power of 1.6 kilowatt. The recoil starter, the lubrication is a splasher. We don't know it is a good splasher for flying because this splasher means that on the crankshaft is like something like a finger, and this is rotating and hits the oil, and the oil splashes through the whole engine. So we have to look, is this a good lubrication or we have to change something? But at the moment it looks perfect. The next thing is the oil capacity. What we have in the engine is 0.25 liter, and the ignition system is a transistorized ignition system. Yeah, it means only that the contact breaker is not direct a switch. So on the ignition coil, you can short circuit it over in the transistor, and you can shut off the engine. And the fuel tank capacity don't care because we remove it. So the optimized engine, yeah. At first I will to say the engine will be like the same as before. We don't mill something on the crankshaft or optimize the crankshaft or optimize the cylinder. We only change something by the parts were mounted on the engine. The one thing is, yeah, we remove the standard fuel tank, and another is that we replace the constant level carburetor. Because the constant level carburetor has, I think, he has some problems when you fly with it, because when you get a low G maneuvers, then the engine gets too much fuel and he can shut off. I know the Spitfire is flying with this type of carburetor, but 90-40 speed, they changed it also to another one. And it gives some different carburetor types where you can use. You can also use a membrane carburetor, like a Vibro or whatever. But by the Vibro carburetor, we use one in our helicopter. It's working fine, but the problem is when you change the height in really short time, then you have to calibrate it, the membrane carburetor. And so for us, it was easier to create an own electrical injection system because we are electronic guys and not mechanical guys. So for us, it was much easier to do go over this way. And another thing, what we do, we drill only a hole in the exhaust system and add a lambda probe there. Now I have to move here something because I can't see the picture. Yeah, now it's better. Do you can see my mouse? I hope so.
Yes.
Yeah, here's the system, how it's working now here. This one is the petrol engine. It's a standard engine. And then we remove the carburetor, but we don't remove the whole carburetor. We only remove some parts of the carburetor. So the fuel, we don't inject direct in the cylinder. So we inject into the airstream of the engine. So we only remove a part of the carburetor, and the fuel or the petrol goes over the same way into the engine like before. So the injection system is only electronics, so it's a processor with some parts, some capacitors, and some resistors, everything else. Then we have some operating elements, like some switches or porté where we can change the RPMs or whatever. And then we have a fuel pump. This is what we need. This is controlled over PWM. Better, it's not PWM, it's a PFM. It's a pulse frequency modulation. They bring the fuel or the petrol from the fuel tank to the engine, and then we have a standard servo motor. It's also controlled over PWM, where we control the throttle valve and the lambda probe. We have some electronic, and then we get the values from the lambda probe back to the ignition system. This we need, that we know how many fuel we have to give to the engine. This is really necessary, and it's a wide range lambda probe, so we can have lambda from 0.7 to 1.6. So and then we can play a little bit how many fuel we give to the engine. And another thing here, we have FM, so frequency modulation input. You can see it on the next picture or next slide. So this FM is going to detect the RPM over Hall sensor. So here on this picture, you see how we test the engine. This is our engine test station. On the right side, it's already known, the engine. The only thing what is additionally now is the PC, where you have some communication over USB, but it's the same what I was talking before. And then we need a test stand or test station. At the university, we have professional test stations for petrol engines, or fuel engines, but the problem is they are not designed for this small kind of engines. Normally they test engines from cars or whatever there. So we have to develop our own test station, and it's a really we did it really easy. So we have the main shaft from the petrol engine here. We go over a clutch to electric motor. The electric motor we change a little bit because I removed the shaft of this electric motor. It's an outrunner engine, so I removed the shaft and replaced a really long shaft there that I can mount it over a lever to a load cell. And we only detect now over the load cell, we detect the torque and we get the RPM. And when we have both values, then we can calculate the power, what we have direct on the shaft. Because when we only use the electric power, then we have some losses from the engine and everything. And when we have, in this case, we have only the losses from the ball bearings. And the ball bearings, yeah, they don't care. Yeah, and then the electric engine is mounted to an electric load. The electric load, yeah, there are some resistors and a lot of transistors on cooling, on heat sinks. Yeah. The engine test electronic, yeah, it's also only a small processor who controls the stuff, or we get the values from it to the PC. And here is also included the DAC to control the electronic load. But at the moment, it isn't a DAC. At the moment, it's an AAC. It's an analog converter. You can call it the porté, or the most guys call it the porté. Yeah, this is how it works, or how we test it. There's also some operating elements like switches or whatever. So go to the next page. I hope we go to the next page. Yeah. Here we can see the engine now with the lambda probe in the exhaust. Then here is the standard servo motor. It's with how we call it in English, a Bowden cable or something to the throttle valve. And here you see the clutch. You also here can see the clutch, and here is now the engine, the electric engine. This part here of the engine here normally is mounted on a frame, but in our case we don't mount it on the frame because we mount it on a lever, and over this lever who press here on the load cell we get the torque. When you don't have the lever here, then the engine can also spin completely free. Normally only this part is spinning free, but we have mounted it like that the whole engine can spin free, and it's only held with this lever to the load cell. And so I have to move it again. Here you see the current sink. What we do, we only we don't regulate the power of the load. We only regulate the current. This had a reason because when you change the RPM of the engine, then it also increases the power. Because when you have more RPM, then the voltage is increasing, and when the voltage is increasing and you have the same current, you have more power. Because in another case, when you regulate the power of the load, then you have the problem. You go faster with the RPM, and the current goes smaller because you like to have the same power, and then the engine can goes up. Can go faster, and faster. This is the reason why you only control the current and not the complete power. Here on this picture, you see our pump where we're using our fuel pump. This is a high precision pump, and this pump you can adjust, but you have to adjust it before you mount it. You can adjust it how many microliters per one pump cycle he transports. You can adjust it from 10 to 20 microliters per one pump cycle. So, where's the next page? So, on next page, we see some test results. There you go. Here in this case, at first what we see, so we see the power in watt. This is this one. This is direct the shaft power or the driven shaft power. Then you see the lambda value. The lambda value I have multiplied with 100 because the lambda normally is only by 1. So that you see it here in this diagram. Then the fuel in gram per hour. What we need actual. Then the throttle valve. The throttle valve is in milliseconds. Yeah. Why is it milliseconds? It's not in degrees. It's in milliseconds because it's only the PWM signal what we use for the servo engine. Then we have the green one is the actual RPM, and the red one is the set RPM. So, and now here you can see we have around about 280 gram per hour by 500 watts, and this is normally what we have for the standard flight for the standard flight condition what we need. And you see it increases, yeah, with the power. We will test it up to 1 kilowatt of power for some, not over hours, but for 30 minutes or something. We let run it up to 1 kilowatt. And this is a really nice picture here, what I find, because there we do a lot of things. Here you can see when we play a little bit with the control parameters. At the moment, at the injection system, it runs a standard PI controller. but we have to change the PI values because it's a non-linear system. So when you have more RPMs and need more power, then you have to adjust the values a little bit. And this is what also what we're trying here with playing with the parameters. A big problem what we have in summertime. Oh, now we have removed this problem, but it was with air bubbles, because the problem is this pumps really hard. So at the beginning, when you start to pump, you get an under pressure, and over the under pressure, your fuel will be get to steam a little bit, to what do you call it, to evaporators or something. So you get really small air bubbles. The air bubbles at the beginning is not a problem because they're so small, but the problem, the air bubbles will collect into the petrol pipe, and when you have a really big a bubble, then the bubble can go with the fuel to the engine, and then you see like this one, that the engine don't get fuel, the RPM goes down, the throttle goes up. He don't shut off when you're not at the highest power. Then he runs. He runs again. But we have removed this problem because we use a check valve, and a check valve normally you don't need much of force to get a fuel through it from one side. So of this check valve we changed the feeder. We replaced it with a harder feeder, and now we have more pressure into the petrol pipe, and with this higher pressure in the petrol pipe, the air bubbles will be collapsed by itself. Yeah. So, and no, this is any more a problem. So yes, now I'm finished. Thank you for your attention. I'm finished. Some questions?
I think we could discuss about all this topic at the end of the presentation. Jörg will end the presentation. You are ready, Jörg?
Yes, I'm here. Thank you. If you pass the control.
Yes. Okay.
Okay, thank you very much for your attention. Thank you for the interesting talks we heard, and I would like to give you some outlook and conclusions from the project, which is now finishing. I think the official end date is March 2021, so there's still some time to finalize some topics and to improve some topics. You see that there is still some ongoing engagement, and that different topics evolve from this project. So again, let me show the basic idea was to develop a low-cost, environmentally friendly and cost-effective long-range UAV, and I think we succeeded in doing so. We've seen two designs which successfully made their maiden flights and went far beyond a maiden flight. Presently, we are at a level where we have automatic flights, automatic start and landings, and we are quite optimistic to further develop these prototypes into application-ready, let's say, technology carriers. So yes, again, let's have a look. We have two designs: the Delta design, the Stork design, which evolved from different perspectives, I would say. If you look at the Stork design, the basic idea, I think, if Renault agrees with me, was to apply a fuel cell engine, fuel cell propulsion, and therefore it's more or less for mid to long range applications, whereas the Delta design evolved from applying or aiming to long range applications where you need to carry a lot of fuel with you and where we need a thermal engine. So we have seen that we successfully derived these designs, built these designs, got these designs into the air, and they successfully fly now. And also, I don't want to forget to mention that our partner from the CNRS successfully developed and manufactured and tested their sensors. So at this stage of the project, we can successfully fly and capture the data for air quality measurements, and further applications are focused now. So we have seen recent activities finalizing the optimization and application of fuel cells, starting to PhD theses on fuel cell application, on the flex fiber investigations. I think very encouraging and very interesting topics. And there is an additional item I would like to present to you, is a follow-up activity, which the project partners, well, we started to think about what to do in the time after the ELCOD project, and we developed together with some new partners, we developed an idea for an extended or for a new project, which we called the ELCOD project, which goes a bit beyond the basic idea. During the ELCOD project, starting in 2017 until 2020, we had the chance to develop two different prototypes for low-cost, long-range solution. And well, if you look at what we've seen today, we succeeded in this. And now we are looking forward to getting these prototypes into real-world application, which means in a follow-up project, we would like to implement these technologies in a real scenario, in real solutions. So we are now at a technology readiness level of something about 5. So we have basic prototypes, basic features, and now we try to establish in this new project, we try to establish some solutions and some applications from basic technology readiness levels from 1, 2, 3 up to a technology readiness level of 6 to get some optimized prototypes and get them into the application of real world use cases. So for this, we got in contact with different partners from different countries all over Europe, and we achieved to get access to 4 different airfields in Iceland, Greenland, and also in Morocco. And for this, we developed an idea for different applications. You see on the bottom here that we have some applications in the transport sector for payload delivery, some applications in search and rescue, operation support, applications in infrastructure monitoring. You can think of flying over railways, flying over electric lines, and so on, and environmental monitoring and research, which is quite close to what we did with the air pollution measurement, but which is extended. For example, we had some guys from interested in volcano research, so they are interested to fly to a hazardous area to take pictures where you normally don't fly with manned aircraft. So in course of this new project idea, we would like to develop some business models for these certain application areas and to further develop and optimize our basic ideas, which means that we have to extend the current state of the project by having some more sophisticated takeoff and landing systems, some more robust and automated systems that we have to further optimize and improve the robustness of the propulsion systems. To develop a de-icing system, we have some very certain or some very interesting applications in the area of Greenland and Iceland. And if you think of flying in those areas, you have to have something like a de-icing system. You have to have special compass system, and for all the applications and independent of the area you fly, you have to have some detect and avoid systems. In addition to, of course, satellite and GSM communication systems, because you have to integrate into the common airspace, and that is something which you have to consider. So that is the basic idea of the follow-up project we are aiming for, and for this we yes, that's something I already mentioned. If you think of okay, there are people talking about delivering parcels by drones. If you think of some commercials you might have seen, that you buy something over the internet and a drone picks up a parcel, brings it to your home. Well, that's something. If you think of multicopters or quadcopters, you're in a quite limited range. Most commercial, what they call long-range UAVs, I think it goes up to a few, let's say up to maximum of 100 kilometers. But what we are aiming for, thinking of ELCOD, UAV is going up to a range of above 100 kilometers, up to a few hundreds, or let's say up to 1,000 kilometers. So that is what we are aiming for in this ELCOD project. So harsh weather conditions, long distance and high endurance, robustness, high payload, reliability, and all of this with having in mind low investment costs, so low cost solution and a robust solution. For this, we were able to get some of our long-lasting partners, let's say INSA, CNRS, in-air solution, and some new partners with quite interesting application areas. For example, the African Institute from Belgium, where you have guys interested in volcano research, some guys from the Iceland University which are interested in transportation issues, guys from Blue Novation, which are some experts in communication and modern platform management, electronic platform communication, image processing, and also partners from Steinbeis, which are experts in European consortium management. And we have on the other side, so these are consortium partners, and on the other side we have partners from the application side. So they are not funded partners in a project, but they can be thought of kind of an advisory board and stakeholders for the applications we are aiming for. So companies from, for example, Iceland, SAR, the Coast Guard. We have the gendarmerie from France for the Renault. Just help me.
Mountain activities.
Yes, it's a mountain police, let's say. Also interested in search and rescue applications. we have partners from Caribou, Greenland, very interesting. They are interesting in herding applications. If you think of Greenland, there you have very wide areas, nearly no population, but they have the need of taking pictures or videos at their reindeer stations to make some UAV herding application. And we also have contacts to the EASA in order to fulfill what is necessary to get into the common airspace, if you think of regulation, standard, and quality. And also some partners, Northrop Grumman, Aerobits, and so on, which brings some experience if you think of air communication systems, detect and avoid systems, and also regulation standards and these things. We already applied with this idea in the funding program, which quite recently ended, H2020, a European funding program. And we got to a very high score for this, but unfortunately we weren't able to get funded. But we will still try to apply in the next funding program, which will start in early 2021. The Horizon Europe funding project or program from the European Union, and we will still try to apply with this idea with these partners for the ELCOD project. So that's it from my side. Thank you very much for your attention.